Connecting a transfer panel with an unswitched neutral to a portable generator with the neutral ground bond creates several dangerous consequences. One is a neutral to ground short fault. The neutral ground bond on the generator connects the neutral conductor, which is the white wire, to the ground conductor, which is the green wire. When plugged into a house circuit, the neutral wire is normally connected to the service panel's neutral bus. If a fault occurs between the neutral and ground wires, it creates a low resistance path for current to flow. The short fault causes a large current to flow, which can overload circuits, trip breakers, or even start electrical fires. A high current flowing on the ground wire can energize metal enclosures, such as electrical panels and appliances. If someone touches these energized surfaces, they can receive a severe electrical shock. The sudden surge of current can damage sensitive electronic devices connected to the circuit, such as computers, televisions, and other appliances. Despite the aforementioned dangers, it is common for transfer panels to be connected to portable generators in this manner because it simplifies the installation process. It also allows the generator to power an entire house, including 240 volts appliances. To mitigate the risks associated with neutral ground bonding, the following measures should be taken. Firstly, use a portable generator with a transfer switch that properly isolates the neutral and ground conductors. Secondly, install a generator interlock kit at the service panel to prevent both the utility power and generator power from being connected simultaneously. Thirdly, ensure that the generator is properly grounded and that the grounding system is in good condition. It is crucial to understand the potential hazards associated with neutral ground bonding and to take appropriate steps to ensure the safe operation of portable generators. Let's delve deeper into why this setup is dangerous and explore the electrical principles at play. In a standard electrical system, the neutral and ground wires serve distinct purposes. The neutral wire carries the return current from the load back to the source, while the ground wire provides a safety path for fault current in case of insulation failure. When a generator with a neutral ground bond is connected to a transfer panel with an unswitched neutral, a parallel path for the neutral current is created through the ground wire. This is because the neutral is already bonded to ground at the main service panel. The flow of neutral current through the ground wire is undesirable for several reasons. Firstly, it can cause electromagnetic interference or EMI, which can disrupt the operation of sensitive electronic equipment. Secondly, it can create a voltage potential between different grounded objects, leading to the risk of electric shock. Thirdly, it can overload the grounding system, potentially damaging equipment and increasing the risk of fire. The amount of current that flows through the ground wire depends on the impedance of the neutral and ground paths. Impedance is the opposition to the flow of alternating current and is similar to resistance in a direct current circuit. The lower the impedance of the ground path, the more current will flow through it. In a typical residential wiring system, the impedance of the ground path is relatively low, which means that a significant amount of neutral current can flow through it. This is especially true if the neutral wire is undersized or if there are loose connections in the neutral circuits. In addition to the problems caused by neutral current flowing through the ground wire, the neutral ground bond on the generator can also create a ground loop. A ground loop occurs when there are multiple ground connections in a circuit, which can create circulating currents that can interfere with sensitive electronic equipment. Ground loops are a common problem in audio and video systems and can cause hum and noise in the signal. To avoid these problems, it is important to isolate the neutral and ground conductors when using a generator with the transfer panel. This can be done by using a transfer switch that disconnects the neutral from the ground when the generator is running. Alternatively, a separate grounding electrode can be installed for the generator, which is not connected to the main service panel ground. This will ensure that the neutral and ground conductors are only connected at one point, which will prevent neutral current from flowing through the ground wire and eliminate the risk of ground loops. It is also important to ensure that the generator is properly sized for the load that it will be powering. Overloading the generator can cause it to overheat and potentially start a fire. The generator should be sized to handle the maximum load that will be connected to it at any one time. It is also important to use the correct type of extension cord for the generator. The extension cord should be rated for outdoor use and should be of the appropriate gauge for the amount of current that will be flowing through it. Using an undersized extension cord can cause it to overheat and potentially start a fire. In addition to these safety precautions, it is also important to follow the manufacturer's instructions for the generator and transfer panel. These instructions will provide detailed information on how to safely operate and maintain the equipment. Ignoring these instructions can lead to serious injury or property damage. Now, let's consider the specific scenario of a 120 volts residential transfer panel with an unswitched neutral connected to a portable generator with a neutral ground bond. In this case, the neutral and ground conductors are connected at both the generator and the main service panel. This creates a parallel path for the neutral current, which can flow through the ground wire. The amount of current that flows through the ground wire will depend on the impedance of the neutral and ground paths, as well as the amount of load that is connected to the generator. If a fault occurs in the circuit, such as a short circuit between the hot wire and the ground wire, the fault current will flow through both the neutral and ground wires. This can cause the circuit breaker to trip, which will interrupt the flow of current and prevent further damage. However, if the circuit breaker is not properly sized or if it fails to trip, the fault current can continue to flow, which can cause the wires to overheat and potentially start a fire. In addition to the risk of fire, the flow of fault current through the ground wire can also create a shock hazard. If someone touches a grounded object, such as a metal appliance, while fault current is flowing, they can receive a severe electric shock. The severity of the shock will depend on the amount of current that is flowing and the duration of the exposure. To prevent these hazards, it is important to ensure that the generator is properly grounded and that the grounding system is in good condition. The generator should be connected to a grounding electrode, such as a ground rod, which is driven into the earth. The grounding electrode should be made of a conductive material, such as copper or steel, and should be of sufficient size to handle the amount of fault current that may flow through it. The grounding system should also be inspected regularly to ensure that it is in good condition. Any damaged or corroded component should be replaced immediately. In addition to these safety precautions, it is also important to educate homeowners about the dangers of connecting a generator with a neutral ground bond to a transfer panel with an unswitched neutral. Homeowners should be aware of the risks involved and should take appropriate steps to mitigate these risks. They should also be instructed on how to safely operate and maintain the generator and transfer panel. By taking these precautions, it is possible to safely use the generator to power a home during a power outage. However, it is important to remember that generators are powerful machines and should be treated with respect. Following the manufacturer's instructions and taking appropriate safety precautions can help to prevent accidents and injuries. Let's now consider the National Electrical Code or NEC requirements related to generators and transfer switches. The NEC provides specific guidelines for the installation and use of generators to ensure electrical safety. Firstly, NEC Section 250.30 covers grounding requirements for separately derived systems, which includes generators. This section requires that a neutral ground bond be established at the generator unless specific conditions are met that allow for the neutral to be switched or isolated. Secondly, NEC Sections 700, 701, and 702 cover emergency, legally required standby, and optional standby systems, respectively. These sections provide requirements for the installation of generators and transfer switches used in these types of systems. Thirdly, NEC Section 705 addresses interconnected electric power production sources, which includes generators that are connected to the utility grid. This section provides requirements for the installation of generators and transfer switches used in grid-tied systems. When installing a generator and transfer switch, it is important to comply with all applicable NEC requirements. This will help to ensure that the system is installed safely and that it will operate reliably. It is also important to consult with a qualified electrician to ensure that the installation is done correctly. A qualified electrician will be familiar with the NEC requirements and will be able to provide guidance on the best way to install the generator and transfer switch. In addition to the NEC requirements, there may also be local codes and regulations that apply to the installation of generators. It is important to check with the local authorities to determine what these requirements are. Complying with all applicable codes and regulations will help to ensure that the generator installation is safe and legal. Now let's talk about transfer switches in more detail. A transfer switch is a device that allows you to switch between utility power and generator power. There are two main types of transfer switches: manual and automatic. A manual transfer switch requires you to manually switch between utility power and generator power. An automatic transfer switch, or ATS, automatically switches between utility power and generator power when a power outage occurs. Automatic transfer switches are more convenient than manual transfer switches, but they are also more expensive. When choosing a transfer switch, it is important to select one that is rated for the amount of current that will be flowing through it. The transfer switch should also be compatible with the generator that you are using. It is also important to consider the type of loads that will be powered by the generator. If you will be powering sensitive electronic equipment, such as computers or televisions, you will need to choose a transfer switch that provides surge protection. Surge protection will help to protect your equipment from damage caused by power surges. When installing a transfer switch, it is important to follow the manufacturer's instructions carefully. The transfer switch should be installed in a dry location and should be protected from the elements. It is also important to ensure that the transfer switch is properly grounded. Now let's discuss generator interlock kits. A generator interlock kit is a device that prevents you from accidentally backfeeding power into the utility grid when using a generator. Backfeeding power into the utility grid can be dangerous, as it can energize power lines that are thought to be de-energized. This can create a hazard for utility workers who are working on the power lines. A generator interlock kit typically consists of a set of two circuit breakers that are mechanically interlocked. The interlock prevents both circuit breakers from being turned on at the same time. One circuit breaker is connected to the utility power, while the other circuit breaker is connected to the generator power. When the utility power is on, the utility circuit breaker is turned on and the generator circuit breaker is turned off. When the utility power goes off, the utility circuit breaker is turned off and the generator circuit breaker is turned on. This prevents power from being backfed into the utility grid. Generator interlock kits are relatively inexpensive and easy to install. They are a valuable safety device that can help to prevent accidents and injuries. When installing a generator interlock kit, it is important to follow the manufacturer's instructions carefully. The interlock kit should be installed by a qualified electrician. Now let's talk about the importance of proper grounding. Grounding is an essential safety measure that helps to protect people and equipment from electrical shock. Grounding provides a low impedance path for fault current to flow back to the source. This helps to trip the circuit breaker and interrupt the flow of current in the event of a fault. Grounding also helps to reduce the voltage potential between different grounded objects. This reduces the risk of electric shock if someone touches a grounded object while fault current is flowing. There are several different types of grounding systems. The most common type of grounding system is the equipment grounding system. The equipment grounding system connects all of the metal enclosures of electrical equipment to ground. This helps to ensure that the metal enclosures are at the same voltage potential as ground. Another type of grounding system is the neutral grounding system. The neutral grounding system connects the neutral conductor of the electrical system to ground. This helps to stabilize the voltage of the neutral conductor and reduce the risk of voltage fluctuations. When installing a grounding system, it is important to comply with all applicable codes and regulations. The grounding system should be installed by a qualified electrician. Let's recap the key points to remember. Firstly, never connect a generator with a neutral ground bond to a transfer panel with an unswitched neutral without taking appropriate safety precautions. Secondly, use a transfer switch that isolates the neutral and ground conductors when using a generator. Thirdly, install a generator interlock kit to prevent backfeeding power into the utility grid. Fourthly, ensure that the generator is properly grounded. Fifthly, follow the manufacturer's instructions for the generator and transfer panel. Sixthly, consult with a qualified electrician to ensure that the installation is done correctly. Seventhly, educate homeowners about the dangers of connecting a generator with a neutral ground bond to a transfer panel with an unswitched neutral. By following these guidelines, you can safely use a generator to power your home during a power outage. Remember that electrical safety is paramount, and taking the necessary precautions can prevent accidents and injuries. Always prioritize safety and consult with qualified professionals when dealing with electrical systems.